Sir Kannan Gopalakrishnan. He was working as a senior architect at Engineering Design Research Centre, L&T Construction, India's largest construction company. He's also worked on projects ranging from institutional buildings to international airports, apartment complexes to aircraft hangars. He's also attended 3 international conferences and 2 national conferences, and has also presented technical papers at the Jawaharlal Nehru University, Delhi, and the MSRIT, Bangalore. He's also won the national championship at Archaman at the India's largest architecture quiz. Sir Kannan Gopalakrishnan currently runs a design firm, Habitat Design Studio, and he is also a visiting faculty at the renowned architecture schools in Tamil Nadu.
Welcome to UGC lecture series. This is AR 6006 Structure and Architecture. We are still covering units 3 and 4, in which we will be dealing with contemporary structural expression through case studies. We are on lecture 14, and if you remember lecture 13, we saw case studies of HSBC headquarters in Hong Kong and Hearst Tower in New York City, both designed by famous architect Sir Norman Foster, and we saw how the structural expression in both the buildings were very unique, and how the whole architecture got enhanced because of the structural expression in which the architect showed the maximum efficiency in. In this episode, we will be looking at a very interesting case study, which is called the InMOS microprocessor factory, designed to manufacture microchips and microprocessors by a famous architect called Richard Rogers. The InMOS factory is a manufacturer of microprocessors. It's a building in Newport, Wales. This was originally built as a microprocessor fabrication plant for InMOS and is now occupied by International Rectifier. The architects of the award-winning high-tech building were the Richard Rogers Partnership. Construction began in 1980 and was completed in 1982. The first look at the building, the InMOS microchip factory, looks something like this. Here you see a small thin structural steel building with 2 big wings stayed by cables. On one side we have clean panels of white, and on the other side we have panels of black and white. This is the first look at InMOS microprocessor factory. InMOS Limited commissioned the famous architect Richard Rogers Partnership, now known as Rogers, Turk, Harbour and Partners, to design its UK microprocessor manufacturing facility at Newport. The design criteria was for a fast construction so that it was ready for operation within 1 year of starting. Here there is one thing we must understand about the architecture of factories and industries. The main thing in designing a factory or commissioning a factory is the business part of it. The architect must understand the business part of the factory, must understand how the factory works, otherwise it is very difficult for the architect to design a factory. And even more important than the functioning of a factory itself is the fact that the production needs to start immediately in a factory, because factory, like a manufacturing site, is a 24/7 by 365 days running unit. A day's capacity of a factory would be any number of products is saleable in the market. So the sooner you start to produce products, the cheaper it is going to be, because all raw materials are going to get costlier as day progresses, number one. Number two is, the sooner the factory goes into production, the more profit the company can get immediately. The return on investment, at the same time the break even point for starting up a business, for setting up a factory, is achieved pretty soon. So for both these reasons, a factory must be started as early as possible, which means that the total design phase of the factory, the construction phase of the factory, and then the commissioning phase of the factory must all be the least possible time. So, with this very difficult brief in hand, what did Rogers do? He started working on the project in such a way that you can start by manufacturing individual components of elements of the factory, and then you can straight away take them all to the site, assemble them, create a factory like a prefabricated design construction technology. Richard Rogers until then was known for designing the famous Centre Pompidou in Paris and the Lloyd's building in London. These buildings were designed in his signature inside out style. We need to understand about the inside out style here, because it is a style which arrived later in the postmodern period of architecture. This style is also known as high-tech architecture. As the name suggests, high-tech and inside out. High-tech as in high technology, where the technological advancement which is required for a building to function is the backbone of any building. That is why the building is functioning, and that is the reason why we are able to enjoy good air, we are able to enjoy Wi-Fi connection, we are able to enjoy all the technological advances that we have. But instead of building a duct or a shaft and then putting all the service lines inside the shaft and inside the ducts, thereby not showing them to the public, was the norm before the era. In high-tech architecture, the architects decided to do something bizarre and something no building had ever done before. They put the functional part of the building, the aesthetic part of the building inside, and they took out all the elements of service structure and all other technological things from the inside, from the duct, and they put it on the exterior. So, all that was usually on the interior of a building are now on the exterior of the building. And the things that was usually on the exterior of the building, like facade treatment, like terraces, the place where you get sunlight and everything, they were all on the interior part of the building. So, such was the concept of inside out architecture. This is what Richard Rogers has tried in this building, and that is what he was also famous for in his earlier projects. The technical requirements were that it would house controlled conditions for the production of electronic microchips, a service area for various offices and a staff canteen, all under one roof. Similar to the brief that was received by our earlier projects designed by Norman Foster and other people, Richard Rogers also got a very interesting brief which said he needs to design a lot of things, but all under one roof. So, this is what Rogers tried to do. The one you see on the top is the elevation of the building, showing the various masts and the way the ceiling, where the roof is held in place. And on the picture below, you see the cut perspective section of the building, where you can see the masts, the A-frames, which are holding all the roof and all the elements upright, and they were producing an entirely big large column free space. Except for these two columns, the entire space is practically column free. Here again, if you see, he tried to use the inside out architecture, where on the outside of the building, when you see from the building from the front, you will see the structural elements which are supporting the building, and you will see all the service ducts, HVAC equipment, AHUs, all mechanical equipment on the outside. You will actually see all of them painted in bright blue, red and yellow colors, situated, kept right in the front of the building. The technical brief demanded highly controlled clinical conditions which are protected from dust and vibration for the manufacture of microprocessors, as well as a conventional office space and a staff canteen. The technical services run externally above a central street supported by a steel framework from which the roof is suspended. The street is the heart of the scheme, linking the clean areas and the dirty areas. Clean areas are the microchip production facility, and the dirty areas are office and support facilities. Here, the architect did one important thing, because the brief said they wanted clean areas for the production, and they wanted other areas like staff areas, like the circulation spaces, the office spaces and everything, which are not all that clean. So architect created clean spaces on one side, the dirty spaces on the other side, and then linked them both clearly with what he called the street. Here is a look at the interior of the building. Even in the interior of the building, we are used to looking at clean facades, clean walls with proper signages. We are not used to seeing all the structural elements here, the framework, the structure on the inside of the building. We are not used to looking at all those things inside the building. Here you see a lot of pipelines, service lines, electrical pipelines. All these things are running on the inside. You can see everything with the naked structure. This is not something which a conventional architect does, but the inside out architecture by Richard Rogers demands this kind of an architecture. That is why this building is noteworthy. The inmost factory was designed to be a model factory that could be constructed in a variety of locations. The speed of the design process and the construction time of the building were critical. The 8,900 square meter single story building was designed to be fabricated off site and assembled on site at Newport. Here, like I mentioned earlier, the architect decided to do one very interesting and very intelligent thing, I must say, because he decides that all the units that are required to build this structure are going to be fabricated at an off-site facility in a manufacturing facility, and they are going to be transported to our site here and then assembled here to create the structure. Also in the brief, it was stated to Rogers that this is a prototype of a building which is going to get repeated at so many different areas, because so Richard Rogers started thinking, if this is a prototype building, this must have absolutely no flaws, it must be flawless in its manufacturing or in the way in its construction methodology. So what he decided, what he didn't want any on-site fabrication, on-site work happening. Very minimal on-site work happened in this project. So everything else was factory produced, which means that they can be produced and shipped to any site in the globe. So that was the specialty of this project again. So here is a look at the clean space and the dirty space that we are talking about. On the right hand side, we see a microprocessor facility where we are looking at a clean atmosphere with a person even wearing clean clothes. On the other side, we see the staff canteen, which is the dirty area. The building is divided into clean and dirty areas, the clean room being for microchip production and the dirty area for all other services in the building. The building has a central spine which is 7.2 meters wide and 106 meters, from which all the services and production area emanates from 8 bays with the potential to increase this to 20 bays. Suspended beams span 40 meters from the central spine with masts along the length of the building, allowing for a post-free area, so providing a flexible interior and the possibility of large work areas. We are mentioning about the clean and dirty areas which are connected by a central spine. Take a look at this section here. This is the street which Rogers is talking about. This entire stretch is the street. On one side you have the clean area, on the other side you have the dirty areas, all connected by central spine. Here is the chip manufacture facility, clean area. This is an office space and a canteen area. So the dirty wing, the clean wing and the dirty wing. This is an A mast. There are 8 such masts, and this building has the capacity to increase from 8 to even 20. So what they would do is 1, 2, 3, 4, 5, 6, 7, 8 of these bays. Each bay is one bay. This area is one bay. These 8 bays has the potential to be converted to a 20 bay facility, which means 12 more bays can be added on to this thing on either of the sides, thereby the function of the building will not get disturbed even if there is an addition happening on this site. Consider the fact that you are building a factory building and that you want to expand the factory building. So, what do you typically do? We start building an additional floor, or we start building an additional level either on top of the existing facility or at the bottom. This kind of a process clearly disturbs the activity of the original factory. Not often the architect designs that in such a way that when you are making an expansion of the existing facility, the original facility will not get disturbed. This is not something which an architect usually considers, but Richard Rogers has considered that point, and that is why he has left the central spine expandable so that it can be even extended to 20 bays in the future. Here is another look at how the building is. Here again you see the central street, services running below and above. You can see all kinds of services which are seen from outside. You see on one side you have the clean areas, and on the other side you have the dirty areas. In the jargon of business, the plant's demands did dictate the design, but the architecture eventually seized control. From the roof, the factory appears to be ruled by geometry. This is what someone said about the factory in a critical analysis in a magazine. The InMOS scheme began as a design for a model microchip factory which could be built quickly as an operational within a year of start on site, quickly in a wide variety of locations, and could be expanded or otherwise adapted without disruption to production. So, here is a look at the structure in which you can see the open pipes and other service elements which are being seen. Rainer Banham, the architecture critic and writer, said of the InMOS factory that it was the first really challenging building of the 1980s. Although the building was commissioned by InMOS for the use, by July 84, Thorn EMI had taken over InMOS. Thorn EMI later sold InMOS to SGS Thomson Electronics. In March 89, the management buyout took out the factory in 99, renaming the business European Semiconductor Manufacturing Limited. In 2002 March, the factory was sold to International Rectifier Company, who are the present day owners of the site. Here is some more pictures of the building, and you can clearly see the structure and service elements of the inside out architecture looking outside. And here you can also look at the steel cables which hold the building's roof in place. Above the street, an exoskeleton of masts provides support to services under the two wings, allowing for a column free and extendable space. Off-site fabrication allows for quick assembly with a flexible system that allows for the use of a solid, opaque or transparent panels in cladding. The first picture which I showed you, the main front elevation picture, yes, you can also see it from here. This is a place where you can change the panels to transparent, opaque or semi-transparent by merely taking out one panel, replacing it with the other. And this is not a very static thing, it is a dynamic thing, because one panel is easily interchangeable with the other panel, just a fix and remove and fix kind of an arrangement, because often when the internal layouts change, it so happens that you also need to change the fenestration. If the internal layout is changing, for example, if there is a place where there used to be a workstation which required natural light, which is going to get converted to a meeting room or a projection with a projection facility wherein you don't require natural light, because when you're going to project something on the screen, it needs to be a decent enough dark room. So, if you're going to change the internal layout of a particular space, the fenestration change also is an important thing which usually cannot be changed if there is a static window, but in this kind of a setup, if even the fenestration could be changed, that is a great additional boon to the users. This is the rough section of the building without any services, without any furniture, and with just one person, just to give you the sense of scale inside this building. look at the arrangement of structural elements here, because this is these two bays, the bay 1 over here and bay 2 over here, are the most important areas of this building, because one of them is the place where manufacturing takes place, and another one is the back office of the entire structure, wherein there are regular office things and cafeterias, administrative, accounts and other standby facilities which are required for any factory setup. On the central space between the two structural elements here, this is the space which Richard Rogers calls the street, and in this space is where it acts as a corridor space which connects the clean areas and the dirty areas on either sides. And imagine if there is one bay of this kind of a structure which has both these wings and the structure, which can be replicated to n number of things based on the requirement, based on the size of the facility. Imagine what we can do in an entire range of things. And there is a structure below, which has below this street, which takes in the service elements, and there are a couple of structures on the top. One is this A mast, and from which there are tendons and other things which support the roof itself, and we also need the support of these elements, because these are the places upon which our entire service setup and everything is going to be positioned here. All the pipelines, AHUs, the air conditioned units, everything is going to be positioned on these two levels here, and you can see all the naked pipelines and everything on to either sides. And from the exterior of the building, you can see the structural elements, you can see service elements and everything on the top. That is the speciality of inside out architecture, like we spoke about. If you could quickly go back to the original images, yes, here is the understanding. In this picture you can have a clearer understanding. This is the street, one of them is a clean room facility and one of them is the dirty room facility. This is the roof which they are talking about, and these are the support systems, and you can clearly see the pipes. Now the same structure, if you could overlay this image on to the image which you just saw, you can clearly understand how the building works and how the building feels for you. Richard Rogers says about this building, architecture has developed from man's need to order the world in space and time, which is a precondition to its being accessible to our understanding. It is problem solving in the environmental field, where logic is transposed into form by art, combining science with art, the practical with the abstract, the measurable with the immeasurable. The science of architecture constantly progresses, science which proves more efficient supplements outdated science. Art in architecture, however, does not make linear progress. It is dependent on symbolism and develops more randomly through philosophical and visual analysis. Art encompasses our hopes and beliefs beyond the limit of the immediate. Here is a night view of the facility, wherein you can see the service elements on the top. This is above the roof, so we are not able to see things which are below the roof. The structural system and the MEP systems is something which you can see here, and on the right hand side pictures you can see the complex structural arrangements which are designed for this building, wherein you can see the different kinds of elements that goes and attaches on and creates the magic that we see over here. Barbie Campbell Cole, another person working with Richard Rogers, said about this building, the building design evolved as a single story steel structure conceived as a kit of rapidly erectable parts with maximum off-site prefabrication to allow the building to be erected bay by bay. The basic concept of phase 1 of the building is a central linear circulation and service spine with internal wings for specialized activities. The spine acts as an internal street or informal promenade, generous enough in size to serve vending machines, public telephones, seating, meeting places, planted areas, waiting areas for the offices, etc. It provides total visual security control and is intended to link up with other future phases of the building on site, so that all the facilities in all the buildings are readily available to all the staff. This is the building and this is the site setting of the building. Look at how beautifully this building is poised with very minimal incision to the landscape around. The CMOS microprocessor facility is a treat to study. Upon this lecture, you will be learning the contemporary structural expressions in factory typology building. We also understood the design philosophies and concepts of architect Richard Rogers. With the learnings that we have got so far from this lecture, you should be able to answer this one question here. Explain the CMOS microprocessor facility and the way Richard Rogers has created the street to delineate clean areas from dirty areas. It was good to have met you with such an interesting case study. I hope to meet you with very different case study in the next episode. Thank you so much.